Welcome to the deep dive. Imagine software that doesn't just respond to your command, but remembers past interactions, makes complex plans, and even takes initiative in the real world, or at least in highly realistic simulations.
Yeah, it really does feel like science fiction sometimes.
But it's quickly becoming reality. Today, we're diving deep into exactly how researchers are building these systems, the fascinating world of LLM-based autonomous agents.
That's right, and our guide today is a really comprehensive survey paper. It's titled A Survey on Large Language Model-Based Autonomous Agents, authored by Lei Wang and colleagues from Renmin University of China.
Okay.
If you want to look it up, and it gives a really systematic look at this field. I mean, it's just exploded with research recently, especially since about 2021.
You can really see it in the publication charts, right? Just a steep climb.
Absolutely, yeah. The cumulative paper count since then has just skyrocketed. It clearly shows the intense interest and, frankly, the rapid progress being made.
Okay, let's unpack this then. Before LLMs, autonomous agents definitely existed, in robotics, game AI, that sort of thing.
Sure, yeah.
But they often relied on complex, maybe handcrafted rules or really extensive training, but only in very limited environments. They were narrowly intelligent, I guess.
That's a good way to put it.
So what changed? Why are large language models, these massive text prediction engines, suddenly the key ingredient for building truly autonomous agents, especially in these broader, less constrained settings?
That's really the core shift this paper digs into.
Yeah.
Traditionally, training agents meant, well, giving them pretty limited knowledge, and they operated within these isolated environments. Think reinforcement learning, trial and error, but in a specific confined space.
Right, like learning one game really well.
Exactly. And that's just miles away from how humans learn, right? We learn for this vast, open-ended, messy world of experience. The big, long-standing problem in AI was always trying to get closer to artificial general intelligence, AGI. Agents that could do self-directed planning, take actions based on goals.
But the old methods fell short.
Yeah, those previous methods, relying on simpler policy functions and restricted settings, they just couldn't capture the flexibility, the depth, the adaptability of human decision-making, especially once you move outside those narrow domains into the open world.
And this is where the magic of LLMs comes in? Or maybe the potential?
Precisely. The potential, exactly.
Yeah.
LLMs, trained on just unimaginable amounts of internet text with billions, sometimes trillions of parameters, they seem to have soaked up this comprehensive world knowledge.
Right.
And they've shown these surprising emergent capabilities, things that look a lot like human-like intelligence, complex reasoning, common sense, creativity even.
Things they weren't explicitly programmed for?
Exactly. So the problem researchers are tackling now, and what this survey really details, is how to harness that power. How do you use these pre-trained language models as the central controller, the brain, if you will, to build agents that can actually exhibit human-like decision-making? Agents with sophisticated memory, complex planning abilities, flexible actions, all within these dynamic, unconstrained environments.
So unlike the old RL agents that needed tons of specific training for one task.
Right. These LLM-based agents could potentially perform informed actions even in totally new situations just by understanding natural language instructions or observations. And that natural language interface, that's a huge game changer. It offers flexibility, and you can actually understand why the H is doing something. There's explainability.
Okay. So our mission today is to get a really holistic understanding of these LLM-based autonomous agents, drawing straight from this expert survey paper. We'll explore how they're being built, what kinds of problems they're being applied to.
Yep, the diverse applications, and also how do we even evaluate them? It's tricky.
Right, evaluation. And the big challenges still ahead. And, crucially, throughout this deep dive, we want to highlight how language powered by these LLMs is just fundamental to all of this, not just as an interface, but as the core processing mechanism.
Absolutely. Language is woven through every aspect.
Let's dive in. All right, first things first. Let's get concrete. How do you actually build one of these agents? The survey paper breaks this down into two main areas: designing the architecture.
Yeah, think of that like the hardware, the blueprint.
And then acquiring the capabilities, the skills, the software that runs on it. Let's start with the architecture. How's it structured?
Okay, so the paper proposes this unified framework. They have a nice illustration, figure 2 in the paper. And it breaks down the agent's mind, so to speak, into 4 key interconnected modules.
More modules, okay.
Profiling, memory, planning, and action. And the fundamental problem this whole structure is trying to solve is this. How do you get an LLM to go beyond just answering a single question? How do you design a system where the LLM acts as the intelligent core, allowing the agent to genuinely behave autonomously.
To perceive, learn, plan.
Exactly. Perceive its environment, learn from it, plan its future steps, and kind of evolve over time. And these modules aren't isolated silos. They're deeply connected. The agent's profile influences its memory, its planning, its actions. It all works together.
Okay, let's take the first piece then, the profiling module. What specific problem is this solving? Why does an agent need a profile?
Good question. This module is all about giving the agent a specific identity, a persona, a role. Maybe it's a coder, maybe a teacher, a domain expert, or even simulating a specific type of person with certain traits.
So, defining who the agent is.
Exactly. And the problem it solves is crucial. An agent needs a consistent identity because who it is fundamentally dictates how it behaves. A helpful assistant agent will respond very differently than, say, a simulated grumpy old man agent.
Makes sense. And you mentioned language is key here.
Absolutely central. These profiles, they're typically written directly in natural language into the prompt that you feed the LLM.
Yeah.
That description, the agent's role, its characteristics, serves as instructions, shaping the LLM's response style, what knowledge it prioritizes, its whole decision-making process.
So the language definition here is the prompt text itself, defining the agent's persona.
Pretty much, yeah.
Yeah.
And the content of that profile, that language description, can be quite rich. It might include demographics, age,
Yeah.
gender, career.
Okay.
You could add psychological info, like personality traits based on standard models,
Yeah.
or even social information defining its relationships with other agents if it's in a simulation.
What you include depends on the goal, I guess.
Totally depends on the application. If you're trying to simulate human social dynamics, then personality relationships, those become really important for making the agent's interactions and language use believable.
And the paper talks about different ways to actually create these profiles, these language descriptions. How do researchers do that?
Right, they outline 3 main strategies, and they all highlight different ways language gets used to set up this identity. The first one is the handcrafting method.
Okay. Sounds straightforward.
It is. It's
Right.
basically manually writing out the profile details you want. You might literally put in the prompt, you are an outgoing and friendly person, or
Uh-huh.
you are an introverted researcher focused on X.
Got it.
The paper mentions the generative agents work, where they manually define each agent's name, personality, goals, relationships, really detailed linguistic profiles to make them act believably in a simulated town. Other examples are MetaGPT and ChatDev, these software development agent teams. They manually predefine roles like product manager, engineer, each with specific language styles and responsibilities.
So assigning roles through written descriptions.
Exactly. And another study manually prompted LLMs with roles like politician or journalist just to see how the language they generated varied, like in terms of toxicity.
Interesting. What are the pros and cons here?
Well, it's super flexible. You can define pretty much anything you can describe in language. But it's obviously labor intensive. If you need hundreds of unique agents, writing each profile by hand gets tedious fast.
Right. So the language is directly the tool, the human writes the descriptive prompt. What's the next method?
The second strategy is the LLM generation method. Here, you use an LLM to automatically create the profiles.
Ah, using the LLM to bootstrap itself, kind of.
Sort of, yeah.
Yeah.
You typically define some rules or a template for the profile structure. Maybe give it a few examples of profiles you wrote that's few-shot learning. Then you prompt an LLM to generate a whole bunch more profiles following those rules or examples.
Okay, so you guide it, then let it run.
Exactly. The paper mentions reagent, where they manually made a few seed profiles, age, gender, traits, movie preferences, all described in language, and then used ChatGPT to generate a larger, diverse set based on those seeds.
That sounds much more scalable for large simulations.
Definitely reduces the manual effort. But the downside is you might have less precise control. The LLM might generate profiles that are a bit inconsistent or don't perfectly match your rules sometimes.
It's no language connection.
Here, the LLM generates the profile text based on the rules or examples, which are also in language. And that generated text then becomes the natural language prompt defining the agent's identity for its later tasks.
Okay, makes sense. Handcrafted, LM generated. What's the third way?
The third is the dataset alignment method. This involves creating profiles based on data from real-world datasets about actual people.
So grounding the agents in reality.
Exactly. The idea is to simulate populations or individuals that mirror real-world characteristics. You take information from a data set, maybe survey responses, demographic data, and you organize that information into a natural language prompt that accurately reflects those attributes.
So you translate data into a descriptive language prompt.
Precisely. For instance, one study profiled GPT-3 agents using demographic data race, gender, age, location, taken from the actual American National Election Studies, ANES. They wanted to see if agents profiled this way would respond to survey questions similarly to the real human participants.
Wow, that's aiming for real predictive power in social
Yeah,
science.
it offers a high degree of realism if you want your simulation to reflect a real population.
Yeah.
Very useful for social science research. The language part is crafting those prompts carefully to translate the real-world data points into a coherent linguistic profile for the LLM.
So handcrafted, LM generated, or based on real data. And you could potentially mix and match these.
The paper suggests that, yeah, you might use real data for current population segments in a simulation, but then manually craft profiles for hypothetical future roles to explore different scenarios.
Yeah.
But however you create it, this profile is foundational. It sets the agent's personality and influences everything else: memory, planning, action.
Okay, that covers identity. Next up is memory. This feels absolutely critical for any kind of learning or consistency. What's the core problem the memory module solves?
You nailed it. It's critical.
Yeah.
The problem is enabling the agent to actually hold on to information it gathers from the environment to build up a history of experiences and, crucially, to use that past knowledge, observations, skills learned, conversations had to guide its future actions.
Yeah.
It needs to be consistent, effective.
So it's not just acting based on the immediate situation.
Right. It needs context from the past. This whole area draws a lot of inspiration from cognitive science, especially models of human memory, how we have short-term or working memory, and how important stuff gets consolidated into long-term memory. Without memory, the agent is basically stateless, restarting from scratch every time. No learning, no continuity.
How do researchers actually structure this agent memory? Does it mimic that short-term, long-term human model?
Often, yes. The paper discusses two main structures they're using. First is what they call unified memory. It basically simulates short-term working memory, and how it usually works is by using the LLM's own context window.
So the memory is just part of the input prompt.
Pretty much. Recent observations, dialogue history, the current task status, that information gets written directly into the prompt for the LLM's next turn. Examples mentioned include RLP, a conversational agent that keeps track of speaker-listener beliefs right in the prompt. SayPlan, an embodied agent, uses scene graphs, language descriptions of the environment, and text feedback as its short-term memory. DEPS, a Minecraft agent, uses the current plan steps, written in language, as short-term memory to generate the next action.
Okay, that sounds relatively simple to implement.
It is, relatively speaking. It leverages the LLM's existing context processing, great for recent info, but the big limitation is obvious: the context window size.
Right, they can only remember so much at once.
Exactly. Current LLMs have finite context windows, which really limits how far back the agent can see or how many pieces of information it can juggle. That's a problem for tasks needing long-term memory or synthesis of lots of past events. And the language here, it's almost all raw natural language text fed directly into the prompt.
So what's the alternative for longer-term memory?
That's the hybrid memory structure. This approach explicitly tries to model both short-term memory for recent stuff and long-term memory for important consolidated info over time.
How do they combine those?
Typically, they use the LLM's context window for the short-term part, just like the unified approach. But for long-term memory, they use external storage, often things like vector databases or other databases.
So memory lives outside the LLM too.
Exactly. The generative agent work is a key example. Short-term context is in the prompt, but past thoughts, actions, observations get stored externally, often as embeddings in a vector store. When needed, the agent retrieves relevant long-term memories based on the current situation, usually using similarity search on those embeddings. AgentSims is another example using this hybrid approach with a vector DB for long-term daily memories. GITM uses short-term for the current plan trajectory, long-term for storing successful high-level plans. Reflection combines a sliding window for recent feedback with persistent storage for insights.
So this hybrid approach gets around the context window limit for long-term stuff.
Precisely. It boosts the agent's ability for long-range reasoning, accumulating knowledge and skills over time. It's crucial for complex tasks in dynamic environments that require recalling distant past events or learned procedures. The retrieval mechanism becomes really important here. How do you efficiently find the right long-term memory?
And how does language fit into this hybrid structure?
It's multifaceted. Short-term memory in the context is still usually natural language text. Long-term memory might store natural language descriptions, but often the retrieval keys are embeddings derived from language. If it's a database, the interaction might involve the LLM translating natural language queries into structured query language like SQL, and then interpreting the results back into language. So language is the interface and often the content, even if intermediate storage uses other formats like embeddings.
You mentioned the paper notes that agents relying only on long-term memory are rare. That makes sense. You always need the immediate context too, right?
Yeah, exactly. Even if you have perfect long-term recall, you need to know what's happening right now to decide the next step. That immediate context, usually handled by the short-term component or the current prompt, is almost always essential.
Okay, so structure is one thing. The paper also talks about memory formats, how the information is actually represented. How does language feature there?
Right, this is about how the memory is encoded. Language is central to several formats. First, and most obvious, is natural languages. The memory observations, agent actions, learned facts is stored just as plain text.
Simple and direct.
Yep. Super flexible, easy for humans in the LLM to understand. Retains all the rich semantic nuance. Examples like Reflection storing feedback critiques as text, or Voyager storing descriptions of game skills in natural language. Here, language is the format.
What else?
Second, embeddings. Here, the information, often starting as text, is encoded into numerical vectors.
So converting language to numbers for efficiency.
Exactly. It makes retrieval much faster, especially with huge memory stores. You can do similarity searches very quickly on vectors. Memory Bank encodes memory segments as embeddings. GOTM uses embeddings derived from language descriptions as keys for efficient lookup. So while the storage is numerical, it originates from and represents linguistic content.
Okay, what about more structured formats?
Third, databases. Storing memories in structured databases, often using query languages like SQL.
Like for factual knowledge.
Yeah, or highly structured interaction logs. It allows for precise querying, updates, deletions. ChatDB uses a database as symbolic memory, with the agent generating SQL. MRKL and OpenAGI integrate external knowledge bases, which are often structured databases. The key language connection here is the LLM acting as the interface translating natural language questions into SQL queries and translating the database results back into natural language for the agent or user.
So language bridges the gap to the structured data.
Precisely. And fourth, structured lists or other formats like trees, organizing information to explicitly capture relationships or sequences.
Like a plan breakdown.
Could be. GITM stores action lists for sub-goals in a hierarchy. ARET LLM converts natural language sentences into structured triplets, subject, predicate, object, for graph-like storage. Again, the input is often language, which gets converted into this more structured format for specific processing advantages, but it's derived from language.
And agents might mix these formats.
Very often, yeah.
Mm.
Like GITM using embedding keys for speed, but storing the actual memory value in natural language for richness. They combine formats to get the best of different worlds.
Fascinating. So memory isn't just storing text, it's about structure and format too. How do agents actively use this memory? What are the operations?
Good question. Memory isn't passive. The paper highlights 3 key memory operations, kind of like how we use our own memory: reading, writing, and reflection.
Okay, let's start with reading.
Memory reading is about pulling relevant info out of memory to help with the current task or decision. The big challenge is finding the valuable information amidst potentially vast stores. How do you pick?
What makes a memory valuable?
Researchers use criteria often inspired by how human memory seems to work. The generative agent paper formalized this with 3 factors: recency, how long ago; relevance, how related to the current situation; and importance, how significant was the event intrinsically.
How do they measure those?
Recency is usually a timestamp. Importance might be a score assigned by the LLM when the memory was stored. Relevance is often calculated using vector similarity, comparing an embedding of the current query or context with embeddings of the stored memories. Some systems use all 3, weighting them. Others rely mostly on relevance for efficiency.
And language is involved in the query.
Often, yes. The query to search memory might be the current natural language task description or an internal question the agent is trying to answer. The retrieved memory, whatever its format, is then often used by the LLM in a language-based way, maybe inserted into the prompt.
Okay, so reading is retrieving. What
Yes.
about writing?
Memory writing is simply storing new information into memory observations, actions taken, feedback received. This is fundamental for learning. 2 practical problems come up here: duplicates and overflow.
How do they handle those?
For duplicates, some systems try to consolidate similar info. GITM uses an LLM to condense similar action sequences into a more general plan. For overflow, when memory is full, they need to discard something. ChatDB allows explicit deletion. RET-LLM uses a fixed buffer with a FIFO strategy first in, first out. Oldest stuff gets overwritten.
And the info being written usually starts as language?
Typically originates from observations or internal states described in language, yeah, which is then stored in one of those formats we discussed.
Okay, reading, writing. What's reflection? Sounds more complex.
It is. Memory reflection is a more advanced process. It tries to emulate how humans don't just store facts, but reflect on experiences to draw higher-level conclusions or insights. The goal is to synthesize more abstract knowledge from raw memories.
How does that work in an agent?
The generative agent work had agents doing periodic reflections. They generate questions about their recent past, like, what have I learned about Klaus? Then query their memory stream, and finally use the LLM to generate maybe 5 high-level insights based on the retrieved memories.
So going from concrete events to abstract summaries?
Exactly. Like going from Klaus wrote a paper, Klaus talked to the librarian, to the insight Klaus is dedicated to his research. It can even be hierarchical, building insights on insights. GITM uses reflection to summarize successful action patterns. Expel reflects on successful versus failed attempts to learn better strategies.
And language must be crucial here.
Absolutely. The process starts with language memories, generates language questions, retrieves info, and then the LLM synthesizes and generates new, more abstract insights in natural language. The LLM's ability to work with language at different levels of abstraction is key.
Okay, so identity via profiling, learning via memory. Next up is planning. How does an agent figure out what to do next, especially for complicated goals?
Right. That's the job of the planning module. The problem it solves is enabling the agent to break down complex tasks into smaller, manageable steps or sub-goals, just like humans make plans. This makes the agent's behavior more logical, reliable, especially for tasks that take many steps.
And the paper categorizes planning strategies.
Yeah, mainly based on whether the agent gets feedback during the process that lets it adjust its plan on the fly.
Let's start with planning without feedback. What does that look like?
This is where the agent generates a plan, maybe all at once or step by step, and then just tries to follow it. Execution feedback doesn't change the plan itself midstream, though it might inform a future plan if the whole thing fails.
Okay, simpler. What are the flavors of this?
They mentioned a few types. Single path reasoning. The plan is just a linear sequence of steps. Think chain of thought, COT prompting, where the LLM generates step-by-step reasoning. Zero-shot ski gets similar results just by adding, let's think step by step, to the prompt. Other techniques like ReWO separate planning from gathering info needed for execution. Hugging GPT decomposes tasks into sequential subgoals.
And language here is?
Language is how the plan is represented. The LLM generates the plan as natural language steps or reasoning. The prompts are structured using language, like code examples, to guide this generation. Then there's multipath reasoning. This allows exploring multiple options or plan branches, more like brainstorming. Self-consistent code generates multiple code paths and picks the most common answer. Tree of thoughts, CodeT, explicitly builds a tree where nodes are thoughts or intermediate steps, and an LLM helps evaluate or select branches. RAP uses Monte Carlo tree search with an LLM acting as a world model to simulate outcomes.
So generating and evaluating multiple language-based options.
Exactly. And the third type is using an external planner. Sometimes for really complex optimization or specialized planning problems, the LLM isn't the best tool. So the agent offloads the planning.
How does that work?
Typically, the LLM translates the natural language cast description into a formal language that a specialized planner understands, like BDDL, Time Domain Definition Language. The external planner solves it, and the LLM translates the formal plan back into natural language steps for the agent. LLM plus P and LLMBP are examples using PDDL.
Language as the translator between the LLM and the specialized tool.
Precisely.
Okay, that's planning without feedback. Seems okay for simple stuff, but probably brittle in complex situations. So how does planning with feedback work?
This is where things get more dynamic and robust. Planning with feedback allows the agent to revise its plan based on what actually happens when it tries to execute actions, or based on other signals. It's much closer to how humans learn and adapt, essential for long, complex tasks in unpredictable worlds. And the feedback can come from different places. First, environmental feedback. This is objective info from the world or simulation itself. Game messages, sensor readings, error codes, observations. The REACT framework is key here. Thought, action, observation loops. The observation, environmental feedback, often text like search results found, directly informs the next thought plan step. Voyager, the Minecraft agent, gets detailed feedback. Progress messages, errors like you need a pickaxe, self-verification results. DPS gives reasons for failure, not just success fail, which is richer feedback.
How is language involved in environmental feedback?
The feedback itself is often described in natural language. Doors locked, collect the 3 wood, error messages. This text gets fed back into the LLM's prompt or state, and the LLM processes this language to understand what happened and adjust its plan.
What other kinds of feedback?
Human feedback. Direct input from a person. Super important for aligning the agent with human preferences or values, or correcting misunderstandings or hallucinations. Inner monologue is an example where the agent can explicitly ask a human for feedback on its understanding or plan, and incorporates that natural language feedback into its next steps.
So humans literally telling the agent what to do or how it messed up using language.
Yep. And the agent uses that language input to adjust. The third type is model feedback. This is internal feedback, where one model, often another LLM or a specialized critic, evaluates the main agent's output or plan.
Like automated critique.
Exactly. Self-refine is one idea. Generate output, get feedback from a critic, LLM, iterate. Self-check uses LLMs to check their own reasoning. Reflection uses an evaluator LLM to give detailed verbal feedback on action sequences, which is more informative than just a score.
And that feedback is in language too.
Usually, yes. The critic model generates natural language feedback like, step 3 failed because tool X was unavailable, or consider this alternative approach. This language critique is then used by the primary LLM to refine its plan or output.
So planning without feedback is simpler, maybe for easy tasks. Planning with feedback is more complex to set up, but way more powerful for the tough, long-haul problems.
That's the gist, yeah. Feedback makes agents much more adaptive and capable in the real world or realistic simulations.
Okay, so we've got identity profiling, learning from the past, memory, and figuring out the future, planning. Now, the agent actually has to do something. This is the action module, right? Where the rubber meets the road.
Exactly. This is the final output stage, where decisions turn into specific actions that interact with the environment. It's influenced by the profile, memory, and the current plan. The paper looks at this from 4 angles.
What's the first angle?
Action goal. Basically, what's the purpose of the action? Is it task completion, like crafting that item in Minecraft or writing that code snippet? Is it communication, where the action is talking or sending a message to another agent or human? Or is it environment exploration, where the goal is just to learn, like trying out unknown commands?
And language relates to the goal how.
The goal itself is almost always defined or understood through language, either a user's instruction, book a flight, or an internal sub-goal, get wood. And for communication goals, language is the action.
Okay, goal. What's the second perspective?
Action production. How does the agent actually generate this specific action command or output? It's not random. 2 main ways. Action via memory recollection. The agent pulls relevant memories first, then uses those memories plus the current context to prompt the LLM for the action. Generative agents did this, retrieving relevant memories before each step. GITM retrieves successful past plans for similar subgoals.
Using the past to decide the present action.
Right. The other way is action via plan. Following the agent just executes the next step from the plan generated by the planning module, assuming no failure signals. DEPS does this following its generated plan unless an error occurs.
And language in production.
Both methods rely on the LLM processing internal states memories or plan steps, which are usually represented in language. The LLM takes that linguistic context and generates the final action command, which might be language or something a tool understands.
Got it. Third perspective on action.
Action space. What actions are actually available to the agent? What can it do? The paper divides this into 2 big categories, using external tools or relying on the internal knowledge of the LLM.
Let's start with external tools. Why use them?
Because LLMs aren't omniscient or perfect calculators. They need tools when they lack specific expertise, need to interact with the real world, or are prone to hallucinating facts. Common tools include APIs, this is huge. Agents calling external services, Hugging GPT calling Hugging Face models, WebGPT querying the web, Toolformer deciding when to call tools, Toolama being trained specifically for tool use, databases and knowledge bases querying structured info like ChatDB using SQL, and external models using more complex models for specific tasks, like Viper GPT generating Python code, or ChemCrow using specialized chemistry tools.
And language is the key to using these tools.
Absolutely. The LLM needs to understand the goal in language, choose the right tool, and then translate the intent into the specific format the tool needs. An API call and SQL query, Python code, all based on its language understanding.
Okay, so tools extend the LLM's reach. What about relying just on the LLM's internal knowledge?
Many actions leverage the LLM's inherent capabilities directly. Its planning capability lets it decompose tasks just using language generation, like Kos and Toti. Its conversation capability means its action is simply generating dialogue. And its common sense. Understanding allows it to make plausible human-like decisions in simulations based purely on natural language descriptions of the situation.
So sometimes the action is just the LLM thinking or talking using its language skills.
Exactly. Language is the capability being used and often the output itself in these cases.
Makes sense. And the fourth perspective on action.
Action impact. What happens as a result of the actions have consequences. They might change the environment, moving things, building things. They might alter the agent's internal state, updating memories, revising plans, learning something new. Or they might trigger new actions, gathering wood, enables building a workbench.
And how does language relate to impact?
The agent perceives the impact, and that perception of the outcome is often represented or described using language. You built a workbench. Error. Insufficient materials. This linguistic description of the impact then feeds back into the memory or planning modules, closing the loop.
Okay, so that covers the four modules of the architecture. Profiling, memory planning, action, all deeply intertwined with language. But you mentioned there's also capability acquisition, the software. How do agents learn specific skills?
Right. Beyond the basic structure, agents need specific abilities. The paper discusses two main strategies here, those that involve fine-tuning the underlying LLM and those that don't.
Let's start with fine-tuning. How does that work?
Fine-tuning means training the pre-trained LLM further, but on more specialized data sets to teach it specific skills or align its behavior for a particular task. The data used for this fine-tuning can come from different sources, again, highlighting language.
Like what kind of data?
One source is human annotated data sets. Humans create the training examples or provide labels. Coh fine-tunes on natural language feedback from humans comparing different outputs, aiming for better human alignment. ATLLM fine-tunes on pairs of sentences and their structured triplet versions to teach language-to-structure conversion. WebShop collected human shopping interaction, data language instructions, and actions to potentially train shopping agents. EduChat uses human-annotated educational dialogues.
So humans provide the language examples for training. What are the trade-offs?
You can get really nuanced, high-quality training data aligned with human intent. But it's expensive and slow to create large data sets this way.
Okay. What's another data source for fine-tuning?
LLM-generated data sets. Here, you use powerful LLMs to create the training data synthetically. Toolbench is a great example. They use ChatGPT to generate thousands of instructions and tool use scenarios from API docs, described in language, and then use that data to fine-tune Llama for better tool use. Another study had agents interact in the sandbox, generating logs of their social interactions in language, which was then used to fine-tune LLMs for social skills.
Using AI to generate training data for AI, faster and cheaper.
Much cheaper and more scalable than humans, yes. But the quality can be uneven, and you might just bake in the generating LLM's own biases or errors.
Right. And the third source?
Real-world data sets. Using data collected directly from actual user interactions or real systems. MyN D2W Web used data from people interacting with real websites to fine-tune web agents. SQL fine-tuned on datasets of real natural language questions paired with their corresponding SQL queries.
Learning from how people actually do things?
Exactly. Captures real-world complexity and often leads to better domain-specific performance. The language data here is authentic user instructions and system responses or actions.
So fine-tuning uses language data from humans, LLMs, or the real world to modify the model. What about acquiring capabilities without fine-tuning? How does that work, especially with closed models where you can't change the parameters?
This is where prompt engineering and mechanism engineering come in, as shown in the paper's Figure 4. They're powerful alternatives.
Okay, prompting engineering. We touched on this. It's about crafting the input.
Exactly. It's all about using the natural language prompt itself to guide the LLM and unlock its existing capabilities. Techniques like chain of thought, tree of thoughts, they work by structuring the prompt with examples or trigger phrases. RLP prompts with beliefs about mental states in language. Retroformer includes past failures described in language within the prompt to guide improvement.
So language is the tool here, programming the agent's behavior through instructions in the prompt.
Precisely. You're leveraging the LLM's sophisticated language understanding to elicit the capabilities you need.
And then the other non-fine-tuning approach.
Mechanism engineering. This involves building specialized modules, rules, or systems around the LLM. These external mechanisms enhance the agent's abilities by structuring the interaction or processing information.
Can you give examples?
Sure. Trial and error mechanisms. The agent acts, a critic, maybe another LLM or rules, judges the outcome, and that feedback loops back, often by modifying the next prompt. Crowdsourcing mechanisms. Having multiple agents debate or discuss using language, converging on a solution. Experience accumulation mechanisms. Storing successful actions or skills, often described in language, in memory or a skill library for reuse, like in GITM or Voyager. Self-driven evolution mechanisms. More complex systems where agents autonomously set goals and improve, maybe using internal rewards or learning through language-based collaboration with other agents.
So these mechanisms structure how the LLM's language abilities are used and how information flows.
Exactly. The critic might give language feedback, agents debate in language, experiences stored using language. The mechanisms orchestrate the use of the LLM's core language capabilities.
Okay, so summarizing construction. Fine-tuning adds deep knowledge but needs data and open models. Prompting and mechanism engineering are more flexible, work with any LLM, but rely on clever design of the language interface and surrounding systems.
That's a good summary.
Now that we know how they're built, let's talk applications. What problems are these language-centric agents actually being used to solve? The paper splits this into social science, natural science, and engineering.
Right, and this is where you really see the power of the LLM's language understanding, reasoning, common sense, and tool use coming together in different domains.
How are they impacting social science, the study of people and societies?
They're becoming really interesting tools here, mainly for simulating human behavior and helping researchers.
Like in psychology.
Yeah, simulating psych experiments or exploring mental health support. One study assigned profiles to LLMs to simulate classic experiments, and the results often lined up surprisingly well with human data, though sometimes too well, this hyper-accuracy distortion. Another looked at using agents trained on Reddit support group posts for mental well-being, finding potential but also risks.
So the problem is finding new ways to study behavior or provide support. And language is how the agents simulate responses or analyze human text.
Exactly. Same idea in political science and economy. Studying voting patterns using agents profiled with real demographic data. Analyzing political speech structures. Simulating economic markets with agents given language-defined traits like preferences or personalities.
The problem being analyzing social dynamics or predicting group behavior, using language to define the agents and process discourse.
Precisely. And a huge area is social simulation, building virtual worlds to study things like how information spreads or just simulating daily life. Generative agents and agent sims created virtual towns where agents interacted based on language, profiles, and memories. Others simulated online forums or classroom dynamics.
The problem here is experimenting with social dynamics safely and affordably.
Exactly. Things you couldn't easily or ethically do with real people. And language is the medium agents chat. Express emotions via language, follow language-based rules.
Even in law.
Yep. Jurisprudence, aiding legal decisions, simulating judge panels, or using agents like chat law that integrate legal databases to answer questions accurately, mitigating hallucination. Language processes legal text, simulates arguments.
And finally, just helping researchers directly.
Yeah, as research assistants, generating abstracts, finding keywords, even helping identify novel research questions by processing literature. All language-based tasks streamlining research.
Okay, a wide range in social science. What about natural science, understanding the physical world?
Here, their language understanding and tool use are key. For documentation and data management, agents can process vast amounts of scientific literature, extracting info from papers to predict material properties, like ChatLFF, using chemistry databases via tools to validate compounds, like ChemCro.
Problem. Handling the data deluge. Language skill. Reading and understanding scientific text.
Right, and as experiment assistants, designing, planning, maybe even executing experiments. That agent automating fluid dynamics experiments using internet info and Python code. ChemCro, again, using 17 tools to plan chemical synthesis based on a natural language goal.
Problem. Automating the scientific method. Language. Translating goals into plants code. Interpreting results.
Yep, and natural science education. Developing interactive learning tools. Math agents that explain problem solving, using Codex to solve university math problems, Code Help for programming education, EduChat for personalized tutoring via dialogue.
Problem. Creating better learning experiences, like
Mhm.
teaching, explaining, conversing, giving feedback.
Exactly. Language is the core of the educational interaction.
Engineering seems like a very natural fit, too, especially computer science.
Absolutely. Agents are huge here, leveraging planning and code generation. In computer science and software engineering, automating coding, testing, debugging. Chat Dev and MetaGPT have entire agent teams collaborating via language to build software. Others assist vulnerability analysis or database anomaly detection using language-based reasoning like tree of thought.
Problem: boosting software development efficiency and quality. Language. Agent communication, interpreting instructions, generating code, a structured language, explaining results.
Honestly. In industrial automation, using LLMs with digital twins for flexible production control, configured via language prompts. Exploring uses in factory automation, even PLC programming.
Problem: creating more adaptive automation. Language. Configuring agents via prompts, interpreting instructions.
And robotics and embodied AI, enhancing robot planning and interaction. Agents using language to understand commands like bring me the apple and planning actions grounded in the physical environment like SACAN. Learning user preferences for tidying from language examples, TidyBot.
Problem: bridging language instructions to physical actions. Language. Understanding commands, generating plans, often language-based, interpreting sensor data, maybe mapped to language.
Yeah, and there are many frameworks like LangChain making this easier to implement.
But you mentioned risks earlier.
Absolutely. The paper stresses this. LLM hallucination is a big one, generating wrong code, incorrect scientific claims, security flaws. Malicious use is another concern. It really highlights the need for robust safety measures and human alignment as these agents become more capable.
A crucial point. So, with all this potential and risk, how do you measure if an agent is actually any good? Evaluation sounds really challenging.
It is super challenging. You're not just measuring accuracy on a fixed data set anymore. You're evaluating complex behavior in dynamic settings. The paper discusses two main approaches, subjective and objective evaluation.
Let's start with subjective evaluation, human judgment.
Exactly. This relies on people assessing the agent. It's vital when you need to measure qualities that are hard to quantify: creativity, intelligence in open tasks, user-friendliness, believability, alignment with human values.
How do they get human judgment?
Two main ways: human annotation. People directly score or rank the agent's outputs or behavior based on some criteria. Like in generative agents, asking annotators specific questions about the agent's believability, or asking if agent interactions in a simulation followed community rules. Language is key because the human reads and interprets the agent's language output or behavior descriptions.
Okay, direct scoring. What's the other way?
The Turing test, or variations of it. Can humans tell the difference between the agent's output and a human's? Like that study checking if people could tell if partisan text was written by a human or their profiled agent. Again, relies on human judgment of language quality and style.
Subjective evaluation seems necessary for capturing the human element, but sounds expensive and potentially biased.
It is. Costly, slow, and evaluator bias is a real issue. That's why some research is exploring using LLMs as evaluators, like ChemCrow using GPT to assess experiment results, or ChatEval having agents debate and critique each other's outputs to simulate human judgment panels.
LLMs evaluating LLMs meta. Okay, what about objective evaluation, using numbers?
Right. This uses quantitative metrics that can be computed automatically. The goal is concrete, measurable insights. The paper breaks this into three parts: metrics, protocols, and benchmarks.
First, metrics. What kinds of numbers are they tracking?
Things like task success metrics, did it complete the task, success rate, reward score obtained, coverage of skills used, accuracy or error rate on specific outputs, like code executability. Higher is usually better. Human similarity metrics, how closely does the agent mimic human behavior or language? Coherence, fluency, dialogue patterns. Higher is better for simulation tasks. And efficiency metrics, how costly or fast is it? Development time, inference speed, lower is often better.
And language gets turned into these numbers how?
The metrics are often derived from language outputs, checking if generated code runs, analyzing text fluency, comparing agent dialogue to human dialogue using linguistic measures.
Okay, so you have metrics. What are protocols? How do you apply the metrics?
Exactly. It's the evaluation setting. Real-world simulation protocols put agents in immersive environments like games, Minecraft, ALF World, and measure performance on tasks within that environment. Social evaluation protocols assess social skills via simulated interactions like debates. Multitask evaluation protocols test generalization across diverse tasks, often defined via language instructions. Software testing protocols evaluate agents on coding tasks like debugging, using metrics like bug detection rate. The protocol defines the playground and the rules of the game,
And language is usually involved in the tasks within these protocols.
almost always. Understanding instructions, generating dialogue, producing code, the tasks themselves are language-centric.
Finally, benchmarks. These are the specific playgrounds.
Yep. Standardized data sets, tasks, or environments for reproducible evaluation. There are benchmarks for interactive simulations, ALF World, Minecraft variants, Agent Bench, benchmarks for social capabilities, Socket, Agent Sims, benchmarks specifically for tool use, Toolbench, WebShop, MobileEnd, benchmarks for programming, like P for penetration testing, and benchmarks for dialogue systems, ClimBench.
And these benchmarks usually provide instructions or scenarios in language.
Right. The benchmark sets up the situation, often using natural language, and the agent's performance in responding to or acting on that language input is measured using the metrics and protocols.
So objective evaluation gives the hard numbers, complementing the subjective human view. Combining both seems necessary.
Definitely. You need both for a comprehensive picture.
So we've covered construction, applications, evaluation. It's clearly moving fast. But what are the biggest roadblocks? What challenges does the paper highlight for the future?
Yeah. Despite all the progress, there are some major hurdles. The paper points out several significant ones.
Like,
First, role-playing capability. We talked about profiles, but getting agents to truly and consistently play specific nuanced roles beyond just a generic assistant is hard. LLMs trained on the whole web might struggle with uncommon roles or accurately modeling complex human psychology, like self-awareness. Language is central because the role is performed through language. Fine-tuning helps, but can hurt general performance. Better prompts might work, but it's tricky.
getting the persona right and consistent. What else?
Generalized human alignment. Standard alignment makes LLMs safe and helpful, avoiding bad outputs. But for realistic simulations, you might need agents to exhibit diverse, even negative human traits to study phenomena like bias. The problem is current LLMs are mostly aligned to one correct set of values. How do you safely realign them for specific simulation goals, allowing them to act out different value systems, expressed via language, for scientific study without making them generally unsafe? It's a tough balancing act.
That's a deep philosophical and technical challenge. Next.
Prompt robustness. Agent prompts get really complex, stitching together memories, plans, context. But LLM prompts are brittle. Small wording changes can cause big output changes. This gets worse when modules feed prompts into each other. Since language is the prompt, its flexibility is also a source of instability. We need more robust prompting frameworks.
Yeah, prompts feel like programming with suggestions sometimes.
Kind of. Then there's hallucination, still a huge issue for base LLMs, and critical for agents. And agent hallucinating could lead to wrong code, failed experiments, security risks. Language carries the hallucination. Mitigation needs things like human feedback loops.
Can't have your autonomous agent confidently making stuff up.
Definitely not. Another interesting one is knowledge boundary. LLMs know vastly more than any single human. For realistic simulation, say recommending a movie, the agent shouldn't use its encyclopedic internet knowledge. It should act based only on what the simulated human would plausibly know. How do you constrain the LLM's knowledge access via language prompts or other means?
Making them realistically ignorant.
In a sense, yes. And finally, efficiency. LLMs are slow. Agents often need multiple LLM calls per action. Memory query, planning step, tool decision, output generation. This cumulative latency makes agents sluggish, especially for real-time interaction or large simulations. Language processing is a bottleneck.
So fundamental challenges in control, reliability, realism, and speed. And language seems to be at the heart of many of them, both the enabler and the site of the problem.
That's a great way to put it.
Wow, okay. That was a truly in-depth look into LLM-based autonomous agents, all thanks to that survey paper by Wang and colleagues. We've really seen how researchers are building these systems, inspired by human cognition, giving them memory, planning, action.
And how language is just woven through everything. Defining roles via prompts, storing memories as text or embeddings derived from text, planning using language-based reasoning, interacting with tools via language commands. It's the nervous system.
And we explored the incredible range of problems they're tackling, simulating societies, aiding science, automating engineering, controlling robots. In every case, understanding and generating language is core to their function.
Yep, and we hit on those big challenges too. Role-playing, alignment for simulations, prompt robustness, hallucination, knowledge boundaries, efficiency. Lots of work still to do.
It's absolutely clear this is a field moving at lightning speed, building directly on LLM capabilities.
So what's the takeaway for you, the listener? Well, as these agents get better and more common, they won't just be chatbots. They could be simulated people, smart assistants, coding partners, even robot controllers. Understanding how they're built, their architecture, how they use language for memory and planning, what they're good at, what they struggle with, gives you a critical lens.
Helps you understand their potential, their limits, and how to interact with them effectively, maybe even critically.
And it leaves us with a question to ponder. As these agents, defined by their language profiles and driven by language-based reasoning, become more common, how will their specific personalities or the language they use shape your trust, your interactions with tech, and maybe even how you think about simulated human behavior itself?
Definitely a lot to think about. Thanks for joining us for this deep dive. We hope it's given you some valuable insights into this really fascinating area.
Until next time.